using titrations to find the concentration of acid slash base. In acid base titrations, we add a standard solution of acid to a measured quantity of base. Pipette slash burettes are used so you know precisely how much acid slash base is used. Indicators added to the base to show you exactly when it's neutralized by the acid. Once you know how much acid is taken to neutralize the base, we can work out the concentration of base. If you use a pH meter, we find the equivalence point by drawing a vertical line downwards until it meets the x-axis. That value on the x-axis is the amount of acid or slash base needed. pH curves, what do they actually do? They plot pH against volume of acid slash base added. So you've got 4 that you need to memorize. pH volume of base added, strong acid slash strong base, pH volume of base added, strong acid, weak base, so it peaks a bit lower. Weak acid slash strong base, pH volume of base added, like this, and then weak acid slash weak base, pH volume of base added, like that. And then you can have the inverse. You can have pH volume of acid added, and in that case, these graphs, let's say you just flip it over. So instead of this, it'd go like this. Instead of this, it'd go like that. Instead of this, it'd go like that. Hopefully you get the point. Vertical part, the equivalence point, aka the end point, when a tiny amount of base causes a sudden big change in pH. Tiny amount of base causes a sudden big change in pH. This is where all the acid is neutralized. Can't use an indicator in a weak acid slash weak base titration because the color change is too gradual. Therefore, it's tricky to see the exact endpoint. Therefore, we use a pH meter. We need an indicator to change color exactly at the end point of the titration. We need one that changes color over a very narrow pH range, lying entirely on the vertical part of the pH curve. Methyl orange, phenolphthalein, red, color at low pH red, phenolphthalein colorless, approximate pH of color change 3.1 to 4.4, phenolphthalein 8.3 to 10, color at high pH for methyl orange, yellow, color at high pH for phenolphthalein pink. Strong acid slash strong base titration. We can use both indicators, methyl orange, phenolphthalein. Strong acid slash weak base titration, we can only use methyl orange. Weak acid slash strong base titration, we can only use phenolphthalein. Weak acid slash weak base titration, we can't use any indicator. We can only use a pH meter. Things to do to ensure the titration results are as accurate as possible. Measure the neutralization volume as precisely as you can. Measure neutralization volume as precisely as you can, the nearest 0.05 centimeters cubed. Repeat the titration 3 times. Take a mean titer value. All results should be concordant. Don't use any anomalous results. Buffer, a solution that resists changes in pH when small amounts of acid slash base are added or when it's diluted. A solution that resists change in pH when small amounts of acid slash base are added or when it's diluted. Acidic buffers have a pH less than 7, and they made from a weak acid and one of its salts. The weak acid only slightly dissociates, and the salt fully dissociates into its ions when it dissolves. Therefore, in the solution, you have lots of undissociated acid molecules and lots of ions from the salts. Basic buffers are made from a weak base and one of its salts, have a pH higher than 7, greater than 7. Salt fully dissociates in solution and weak base only slightly dissociates. The solution contains lots of base ions and acid molecules. Shampoos contain a pH 5.5 buffer. Human hair, because it becomes rougher if exposed to alkaline conditions. Therefore, the buffer and the shampoo stops it from happening. So that's a really good example. Biological washing powders contain buffers, keeping the pH at the right level for enzymes to work efficiently, 7.4, therefore containing, and also biological buffer systems in our bodies, making sure our tissues are at the right pH. For example, blood stays at pH close to 7.4, therefore it contains buffer system. Diprotic acid, one that can release 2 protons when in solution. When the acid reacts with a base, it is neutralized, obviously, as the reaction happens in 2 stages. 2 protons are removed from the acid separately in the diprotic acid. Therefore, the pH curve has 2 equivalence points. And that's really important because I feel like in the exam, obviously, they could give you a pH curve, and pH curve plots pH against volume of acid slash base added, pH against volume of acid slash base added, and it could give you 2 equivalence points. And because you've never seen that before, you're just so used to these that you've learned, reviewed, and memorized, you're like, why is it 2? And then it could say state which type of acid it is, and it'd be a diprotic acid because the 2 protons are moved from acid separately, therefore the pH curve has 2 equivalence points.